So here I'm going to finish up talking about the important properties for pollutants by talking about persistence. So what is essentially the propensity of a chemical substance or pollutant to resist chemical and biological breakdown. So chemical breakdown is things like hydrolysis, oxidation, photodegradation that you might remember from chemistry. Biological is just being metabolized by organisms, used for energy, or in other words, decomposition. So we characterize persistence using primarily residence time, half-life, which we've talked about already a little bit when we talked about radioactive pollutants, and bioaccumulation, which we'll just touch on really briefly here and talk about more later on in the course. Okay, so first we're going to talk a little bit about residence time. So residence time is the average amount of time that a chemical spends in an environmental compartment. So an environmental compartment is just whatever you're interested in learning the residence time of. So in this example down here, it's a lake. So we're interested in how long is a molecule of a pollutant going to spend in that lake, for example. But it could be a stretch of river, it could be the air above a city, whatever it is you're interested in. So to calculate residence time, we need to know that the compartment that we're interested in is in what we call steady state. So what does that mean? It means there's no change in chemical concentration of the pollutant that you're interested in within that lake or unit of air or stretch of stream. So that is pretty similar to equilibrium conditions, but the main difference here is that for steady state we've got an open system. So that means that we've got inputs, in this case pollutants going in, and outputs, in this case pollutants going out. So this is an open system. And when we're talking about equilibrium, we're talking about a closed system. So there are not inputs and outputs. So that's the main difference between steady state and equilibrium. So the main equation that we're interested in when you were thinking about mass balance, which is really what we're talking about, and we'll touch a little bit we'll touch more on that later on in the not too distant future. But the main equation is that change in mass of, in this case, the pollutant in the lake that we're interested in is equal to the mass coming in, or inputs, minus the mass going out, or mass outputs. So if the amount coming in, right here, is equal to the amount going out right here, then there's no change in mass of the pollutant within the environmental compartment, or in this case, the lake. So you can see that if the same amount is coming in as is going out, you're always going to have 1.5 kilograms of pollutant in that lake. So if you have steady state, then you can calculate residence time, and it's pretty straightforward, I hope. So you use the mass in the lake and you divide it by the input or output rate, it doesn't matter, they're the same. And this will give you the average number, in this case, of days that a molecule of pollutant stays in the lake. So if we were just to do that right here, figure out the residence time, we'd have 1.5 kilograms. But since the inputs and outputs are in grams, we'll just convert that into grams. So you have 1,500 grams. We'll divide that by the input rate, 0.5 grams per day, and you end up with an average residence time of 3,000 days. My handwriting has looked better, but hopefully you get the point. Okay, so just sort of to review and think about this, pre-industrial atmospheric carbon dioxide was in steady state, and pre-industrial is this period of the figure right here, the Industrial Revolution being here, and then after that we've got CO2 increasing. So this means, when we say that it's in steady state, this means that either A, the concentration of CO2 in the atmosphere was constant, or does it mean B, no carbon dioxide entered the atmosphere, or C, the climate was constant? So you can pause and think about which one of these answers you feel is correct. Okay, so the most correct answer is that the concentration of CO2 in the atmosphere was constant. So there was CO2 entering the atmosphere through respiration, plant respiration, soil respiration, and just like it was leaving the atmosphere through photosynthesis. It's just that those two fluxes, the amount going in was equal to the amount going out, so the concentration of CO2 in the atmosphere was constant. And the climate wasn't constant because there were other things influencing climate over time, other than just the amount of greenhouse gases in the atmosphere. Okay, so here is our first example problem, looking at how to calculate residence time, or perhaps the second one if you thought that first little sort of lake problem was a good example. So we want to calculate the residence time of atmospheric carbon before the Industrial Revolution, so pre-industrial residence time of atmospheric carbon. So here we have the compartment size, or the mass of carbon in the atmosphere. So to get residence time, I'm just going to abbreviate it RT. Oh, that's pretty messy. Okay. RT equals the mass in the compartment. So it's 600 gigatons divided by, here's the inputs to the atmosphere, 174.6 gigatons per year, and that's from soil and biota respiration, so trees, animals, and all that, and ocean exchange. And here are the outputs. You'll notice they're the same, and that's from photosynthesis and ocean exchange. So you can choose either one of those. We'll just say I'm using inputs, and so you're dividing the mass of the pool by 174.6 gigatons per year, and you end up with 3.4 years. So that is essentially residence time, and the next little video that we'll look at deals with half-life.